Hey folks, welcome back to my YouTube channel. So today I have a Kubernetes pod that has this Quen model, which is a 4 billion parameter model. This is running inside a Kubernetes cluster. This is how I interact with the pod. So I'm sending a curl request. This is my query, how to grow my YouTube channel. Give me a max of 100 tokens. So watch this, right? See, there's 8 gigs of memory already loaded. My VRAM has, I have like 16 gigs of VRAM. My GPU utilization is currently at 0%. So when I send that query, let's see what happens. So the GPU utilization should go up. And as we see, it's going up from 36. And then it might go up a little bit more. Yeah, 41, 42, and boom, I get my response. So it says, to grow my YouTube channel, it requires a mix of consistency, strategy, engagement, and blah, blah, blah. So how do we make that happen? That's what we're going to talk about today. And we will run the exact same model in a bare metal GPU as well. And we'll see what kind of differences we see in performance and how, and how much technical debt do we carry for this. Hey folks, so we saw the Kubernetes setup, right? So for this to work, what I have is I have a Kubernetes pod in my cluster, which has a config map where I've defined the model name. And then I have an image in my Docker hub with all the dependencies that it needs to interact with the GPU. And then there's a service. So I interact with the pod using the service, right? But I do a port forward on the local host so that I don't need to use the service IP. I can just use my localhost IP and then I can interact with the model that way, right? So the other thing that I want to talk about for today is that, so we get all of our models from Hugging Face, then we'll run it in a GPU. There will be no container involved here. And then the other setup that you already saw is going to be in a Kubernetes cluster, right? So another thing to note today is that, so model weights are, let's say like if we have a model that where the model weight is 6 gigs. So when that model gets loaded in my VRAM, that's going to consume 6 gigs, right? But there will be some extra runtime overheads like KV cache and activation that can consume anywhere from 0.5 gigs up to 2 gigs, but it can be more depending on the context size. So it's not a hard limit, it's a variable and just an example for here, right? So the other thing I wanted to mention is token as well. So when we mentioned that token equals to 50, so in English word, it roughly means that it's 0.75 words. So it's going to, like, that's going to be the calculation. It's going to be 37.5 words. So if I give something like max new token is 256, I'm telling the model that, okay, I need a response from you, but the maximum words that it can generate is that. And then based on the token size, the KV cache and activation value increases as well, right? So the other thing we need to note is what kind of tensor type is the model, right? Is it FP32 or is it BF16? So the difference with FP32 and BF16 is that, so for each parameter, it consumes 4 bytes of space. So if it's 4 billion times 4, it's going to consume 16 gigs. If it's, BF16, 4 billion times 2, it's going to consume 8 gigs, right? And one behavior I noticed was that if we don't explicitly mention the type, in this case, these two parameters, then the model, like the transformer loads the model in float 32. So essentially it's loaded in CPU first and then it's moved to the GPU, right? So the exact same model can consume 16 gigs of memory if we don't mention the float type. Or if we mention the float type explicitly, it's going to consume 8 gigs of memory. And then there's runtime overheads, right? So the model that we're going to interact today with is Quen 4 billion, and then you can see this is a BF16 model, so we can see the tensor type over here. And then when we go to files and versions, we see that there are 3 different model weights, which roughly comes to be 8 gigs, right? So I did download I did create a new machine from Bash.ai. I connected to it, and then I ran my GitHub repository code. So if you clone this repository, GitHub Fast AI, I will link this in the YouTube description. There's this command here. So Kubernetes single node cluster setup, and then run all.sh. Once you run that command, it downloads everything it needs to make the machine, kind of ready enough to go with Grafana, Kubernetes, and all other dependencies. So let's wait for the installation to finish. Okay, so all of my dependencies have been installed. So once all of this is done, I need to activate my virtual environment. So just copy that line and then we have it downloaded. So let's get this to full screen actually here. Okay, so I need to go to GPU vars.ai and then I need to go to, so let's do the bare metal test first, right? So what I'm going to run in this window here is going to be watch on NVIDIA-SMI, NVIDIA.SMI. So we see that we have a 16 gigs VRAM, right? And then the current GPU utilization is at 0. So once I'm here, right? So there's this run model default.py, right? So in this one, I haven't mentioned the D type. So this will load the model by default to being as F32 model. And then if we have a look in the script here, so actually let's do a cat on model interaction. So essentially there are two variables that I need to declare, right? So that script loads this variable, this environmental variables. So let me copy that part here. So export model path, and then so that variable can be seen from our Hugging Face, right? So let's go here and then see, when you go to the model and just double click that part, right? If you want to interact with a different model, for example, text generation, well, it has to be text generation transformers for this exact script to work. So let's say if you want to work with Moonshot AI, then just copy that and that's your variable. That's it, right? So the reason I'm doing this is because the script will download the model on its own. I don't need to go ahead and perform a manual download. So just copy that part, and then that's done. And then let me declare the max new tokens as well. So okay, 120. Let's confirm that we have the model defined. Export model underscore path. Okay, yeah, so we see the model path. We have the token defined as well, right? So let's run the script, and then let's go Python 3 run model default.py. So let me actually pull this up here, and then let's talk about this, right? So as I mentioned in this script, I haven't explicitly given the float type for my model, right? Even though this model we saw previously is an FP16 model, right? It will be loaded as FP32. So it will end up consuming 16 gigs instead of 8 gigs, right? So let's go ahead and run that. And if that model is not downloaded, right, it will detect that it needs to download it, and then you know, like, it will do all the loading part on its own. So for my prompt, how to grow my YouTube channel in 2025, I'm going to stick with the exact same prompt. So we can see here right now it's downloading the model. We talked about 3 different weights, one being almost, you know, 2 of them being almost 4 gigs, another one was 100 MB. So it's downloading that. And then you can see that, you know, like as of now, it's not loaded into my VRAM, neither it's utilizing any memory, because we see that it's just, you know, 2 megabits, and then utilization is 0%. So once the model is downloaded, right, it gets loaded as well. You can see that, you know, it did load in the shards, and then see the memory went up to almost 16 gigs, right? And then it kind of gives an output here as well that it took around 47.88 seconds to load the model on CUDA, because it had to download it, right? And then based on the context, based on the max token, it gave me an output. So see, the memory allocated is 16.09 gigs, and it's, you know, almost reserved was 16.11, even though it's an 4 billion parameter model, right? Because if we go control our echo model path, we downloaded Qwen 4 billion model, right? So now if I run the exact same model where I have defined the BF16, so if you want to look at where I defined the BF16, it's essentially, let's just go here, D type, and then see here, that's where it's defined as float 16. So that is the responsible part with this. And then on top of that, like, we're not compressing the model by any chance, right? By default, this model is, you know, let me copy the model name again. So Qwen. Okay, by default, this model is a BF16 model, right? So see that tensor type here. So I'm not performing any kind of compression at all. So let me run the script now, and then let's go Python 3 run model bf16.py. Sorry, Python 3. Okay, so now to load the model in the CUDA, it's not going to take 47.88 seconds because we've already downloaded the model, right? So it's asking me enter your prompt. So let me copy the same prompt again, how to grow my channel in 2025. And then, okay, it's loading the model. See, when it loads this checkpoints. So the memory consumed is not going to 16 gigs like it was before. And then the model got loaded on CUDA in 2.2 seconds. See, the memory allocated 8 gigs as well, right? Here it took 47.88 seconds because it had to download the model first, and then the memory allocated was 16 gigs. So now it's done with the context, right? So there we go, that's our answer. So that was one point that I was trying to make over here. So if you don't define the float type, by default it gets loaded as FP32. If if you define it, then it's going to consume less VRAM for you, but you need to know you're not doing any compression, right? If it's an FP32 model, maybe let's just load it as FP32, but if it's FP16, it's okay to use FP16, right? So let's actually make a note of this, and then let's see, it consumed that amount of memory. So let me just paste this here. Okay, so now we will do the exact same thing, but we'll do this from a container, right? So let me open a completely new clean session. Let's SSH into this again. It should be here. And let me actually open a TMOC session to make my life easier. Okay. And then let me give another one, SSH. Okay, so to run this in a container, all we have to do is go to gpu.vast.ai and then cd inside container GPU. So you will see there's like the Docker file, there's app, and there's Kubernetes folder. So go inside Kubernetes folder, we'll see a config map, a service, and deploy.yaml, right? So we spoke about this here. Let me just go back a bit more. So this is why we have all of these components, right? So let me go ahead and go kubectl apply -f. Before I do that, I kind of wanted to show to you that if I go veeam config map, see the model path here, it's Quinn, right? So just if you want to interact with a different model, just change that variable, that's enough. And then let me go kubectl apply -f config map, and then let me create my service, kubectl apply -f service to the YAML. After I create my service, let me run a kubectl get parts -watch. So with watch command, like it basically runs that kubectl get part command every 2 seconds, so we don't need to run it all the time. And then let me run kubectl apply -f deploy.yaml. Okay, so it's creating a pod. We see that's the pod it's trying to create. It's still on pending state. And then okay, it's moving to container creating state. So briefly, like, if Kubernetes is a new concept to you, so ConfigMap is a way we store our variables, right? So why would you need something like this? For example, imagine a situation where you have like say 3 different parts, right? And there's the exact same variable that you need to use all the time, that variable being color as blue, right? So let's say something happens and we want to change the color to green. So if you define that in your part spec instead of defining in a thing like a config map, you need to go and change the spec and this part and say that, hey, listen, the color is green now, it's not blue anymore. Do the same thing here and then here. Imagine if you have 1,000 parts, it's literally impossible to change all of those values, right? So instead of that, what we do is we create a config map. So we define a value over here, like color is blue. If we need to change the color from blue to green, we just redefine the variable here once, and then we will kind of mention in our pod deployment that, hey, you need to get that color variable from this config map. So after that, if we need to change the color of the pod or because of some reason the variable value gets changed, just restart the pods and it will load the updated value. So in my current setup, I did define it like this because if I want to work with a different model, I don't need to go ahead and mention it in all of my pods. Just change my variable and that's enough, right? So, and if you notice this, it's taking a while for the container creation to complete because what's happening is I have my image in Docker Hub. So that image is a big enough image because, it has CUDA context and many of the dependencies that it needs to run a GPU, right? So that's why this is a bigger image. I think I might have an image here. Let me check Docker images. Okay, see, that's an example. So there are like different versions. So some of them are like 9 gigs, some of them are 7 gigs, right? These are big enough images. That's why it takes a while for the download operation to complete. So we can go and run kubectl describe pod and then Okay, there we go. So the pod is running now. So the other command that I kind of wanted to run was nvidia-smi. So see this, right? As of now, the pod is running, but it's not consuming any memory because the pod is running, but it hasn't completed downloading the model itself, right? The pod needs, so, during the pod creation, all it does is that gets the image, right? And then that image has all the things that it needs to interact with the GPU. After that image is ready, then the pod needs to go ahead and download the model itself, right? So after the model is downloaded, it will be loaded in the memory all the time. When we did it with the bare metal setup, like the model is only loaded into CUDA because see, that's what we saw, right? So it's not actively in the memory, but once it's loaded, then only it will be in the memory. But we see the memory is going up now because the pod has completed its part of downloading the model, right? So now, while I'm here, let me go ahead and run the model interaction.txt. So if you remember this part here, I said like I'm going to do a port forward on my local service so that I can interact natively with my model. So let me go ahead and run that. But before I run it, I'll add this ampersand sign so that essentially this will move the process in the background and I get the cell for myself. If I don't do that, what happens is it will keep running and then I have to either open a new terminal or if I want that back, kill it. But that way it runs in the background, I have the session back, right? So now let me cat that file again, cat model interaction.txt. So there's one thing I want us to keep an eye on, right? So when we run the model before in a GPU itself without any container or any pods, our model memory allocation was around 8.04 gigs, right? So here you see that 7.8 gigs is doing the job because it's just the model weight that's been loaded so far, right? There's no query that we have sent which will have kvcast and a bunch of other runtime overheads. But when we send this query, we should see some difference, right? So, and actually let me send the exact same query and then the exact same token as well. I think my token was probably 120 tokens. Yeah, so max new tokens is 120. So let me run this curl here and okay, so let me change a couple of values. Let me change that to 120, and then let me change this prompt to, okay, let's go. So how to grow my YouTube channel in 2025. Okay, so let's see. So the memory went up from 700 and 7800 to 7900 almost. Let's save that here. Okay, let me just move this here a bit. So that's it. Now my query is resolved and then I can see the memory went up a little bit more, but it didn't even touch 8 gigs, right? So let me send that query again. Let me increase the token size. So this is what I meant, right? When you increase the size of your token, the response is going to increase as well, because the same math that we did here, right? It's going to be roughly, the number of tokens times 0.75 words. So let me try 2000 token. So let's see if the memory increases as well, because we just increase our token size, and or it might, that memory might be enough to do the job. Okay, so and then yeah, so the GPU utilization is not necessarily maxing out. It's kind of around 3800. So we see the memory increased a bit, right? So see, it's at 7954. So let me just make a note of that as well. So 7954, 7968. Okay, it's climbing up. So the reason it's climbing up is because the token that we're using is higher, right? And then if we have a look at this graph, we said that model weight is going to be loaded in the memory. That's going to consume VRAM. On top of that, kvcast and activations are going to consume extra, right? So kvcast will increase, the key value cast essentially will increase if our token increases. See, we're going all the way up to 8100 now. So initially for a 120 token, the max memory utilized was 7.9 gigs, but now we're seeing all the way up to 8 gigs of memory utilization. And then let me just paste that here as well. Okay, so it's still doing its inference. It's not completing yet because it's it is a big token for this particular model. So the utilization is 42. So let's give it a moment, and I hope it gives me an amazing plan on how to grow my YouTube channel as well, hopefully. So okay, yeah, I think like this is another thing that I kind of need to look into, right? Like, I mean, I would have expected, for example, 80% GPU utilization and then complete this particular inference faster because I have more memory if it needs more memory. But I think that's it with the memory, right? Like, there's no point of using more memory than this. But GPU utilization could be increased. But I think this is something that I will dig deeper into my future labs. That is there any throttling that's going on because of which the GPU utilization is not going up, or maybe just the nature of the model that it uses that and it maxes out. And then on top of that, right, like it's a bit slow because it depends on what kind of GPU I'm using as well. For my particular use case, we know I'm using a 4060 Ti from RTX. It's not a slow GPU by any chance at all, right? Like, the VRAM is big enough. It has one GPU to the job, and okay, it's actually still loading. Okay, but yeah, I think like for instance, if I were to use more GPUs, right, then will it be faster instead of one GPU? Like, the exact same spec but 2 GPUs. Do I get the answers faster? Those are the things that I kind of want to discuss later on. And then the next thing that I'm going to interact with is VLLM. So VLLM, so I think this is a project that people use in their production, right? So it's as it says here, it's a high throughput, memory efficient inference and serving engine for LLMs. So this is the topic for the next video, and this is how things are done in production. So it will be important to understand how the setup works as well. But okay, here we go now. So it's finally completed with all of my inference. My utilization is down to 0%. So let me see the response, and there we go. Yeah, it is a long enough response, but essentially we'd like to see that completed a bit faster, but it is what it is, right? So it's giving me a bunch of options. Can reduce production time while maintaining quality, and then who is my idle viewer? Okay, so there are a couple of questions that I need to answer to grow my YouTube channel, and yeah, I think that's what I wanted to talk about today, guys. And I think like in a summary, right, running the exact same model without a container almost consumed 8 gigs of memory for me, right? When I ran NVIDIA SMI in a loop, I saw up to 7.9 gigs being consumed. Oh no, actually this is for the container, right? So this is for the bare metal, for the GPU itself, no container. That took 8 gigs. Running it in a container took 7.9 gigs. So there is not much of a technical debt when I run the model inside a container, right? I mean, there are some complexities that comes with running this model inside a container, but those are not massive complexities. We know how to work with Kubernetes. There are many resources with Kubernetes, and running this in Kubernetes gives me so many more advantages. Like, an example was ConfigMap. There are many things in Kubernetes that can make our life much more easier when we work with, like really high number of machines, right? So if I had like, for example, if I was consuming way more memory here, less GPU utilization, I would be worried, but that's not the case at all. So I think running inside a container is actually quite an efficient way to run my models. It actually even consumed less memory in my case. So maybe it needed small CUDA context, right? Compared to the bare metal stuff. Anyways, that was my point today. So thank you for watching, and I'll see you guys in the next video.